Hello, welcome to this module in this massive open online course. Alright, so we are looking at classification of systems and their properties. So let us continue our discussion on the various kinds of systems. So another important class of systems is what is known as linear systems. Alright, so another very important class of systems which we will frequently encounter and which we will almost always encounter is that of linear systems. Now a system is linear. Now the system T is linear if it satisfies the following properties. Now the first property is what is known as additivity. Additivity is very simple. Consider two input signals x1t, x2t such that input x1t, that is t of x1t equals y1 of t, that is input x1t produces y1 of t, input x2t produces, let us say, output y2t. Now the system, the additivity property or the system satisfies additivity if this implies t of x1t plus x2t, or if this implies t of x1t plus x2t equals y1t plus y2t. That is, if x1t produces the output y1t, x2t as input produces the output y2t, then if x1t plus x2t produces the output y1t plus y2t, and this is true for all possible inputs x1t and x2t, the system is said to be additive. Okay, and this has to be true for all, not just a chosen x1t, but true for all x1t comma x2t. Okay, this has to hold true for all x1t, x2t, and if this is satisfied, this implies the system is additive. Okay, our system is additive. System satisfies additivity. The system satisfies additivity property. Now similarly, now the next property is what is known as homogeneity. Homogeneity simply implies that if x1t produces the output y1t, this implies t of alpha times x1t produces the output alpha times y1t, or let us So, alpha times x1t, or you can simply write it as xt and yt. That is, if any input xt produces output yt, alpha times xt produces the output alpha times yt, where alpha is any scalar quantity, right? Alpha is any number. Implies any basic number, either can be real number for real sum signals or can be a complex number for complex signals. So, scaling by a scalar quantity alpha, if the input is scaled by a scalar quantity alpha, then the output is also scaled by a scalar quantity alpha. If the system satisfies this property, it basically satisfies the homogeneity property. Okay, so this is the homogeneity property. This is the homogeneity. Okay, and systems that satisfies, now a linear system is simply one implies it satisfies both additivity plus homogeneity. That is, linear system satisfies both the properties, that is additive and homogeneous. Linear system satisfies both properties, that is additivity and homogeneity. Okay, so such a system is known as a linear system if it does not satisfy, otherwise it is known as a non-linear system. Linear system satisfies both the properties, otherwise it is known as a non-linear, otherwise it is a non-linear system. So, this is a linear system, non-linear system does not satisfy either property or both properties. Okay. So, a linear system is one that satisfies both the additive properties, that is, if you add two input signals, the resulting output signal should correspond to the sum of the output signals of these two input signals, and if you scale an input signal, the resulting output signal should be correspondingly a scaled version of the output signal. Okay, and a system that satisfies both these is known as a linear system. And for example, let us take a very simple example, yt equals dxt by dt. This is known as a differentiator. You can see that this is a linear system. This is a linear system. Okay. Now, if you take for example yt equals 2x square of t, this is clearly, this is a non-linear system. You can check that it will not satisfy the properties that are related to linearity. Okay. So, that basically is the definition for a linear system, which, as we said, is an the class of linear systems is a very important class of systems, because most of the time these are the kind of systems that we are going to be encountering. Another important class of systems in the same vein is what is known as time invariant systems. All right. So, the class of time invariant systems. Okay. So, time invariant implies if t of x t equals y t, that is if input to system x t gives output signal y t, if this implies t of x t minus t naught equals y of t minus t naught, and this holds for all shifts t naught and for all input signals x t, that is for any, or let us put it this way, x t minus tau, x t minus tau equals y t minus tau, that is for any shift tau, that is if input x t yields output y t, correct, if input x t yields output y t, then if I shift it by tau, x t minus tau is basically a delayed version, okay, of x t, okay. If I shift x t minus tau, then the output y t is corresponding, it yields an output signal y t which is correspondingly shifted, okay. So, this is x t minus tau, this is shifted input, and this is basically y t minus tau is basically which is shifted output. Of course, if tau is positive, it is a delay, if tau is negative, then it is an advanced signal. So, it is a shifted. If it satisfies this property, such a system is said to be time is a time invariant system, otherwise it is a time variant or a time varying system, else it is a time varying system. Else it is a time varying system. Else it is a time varying system. For example, again let us take another example. If you have y t equals minus infinity to t x of tau d tau, x of tau d tau, you can show this is time invariant. For instance, if you substitute x of t minus tau, let us call the output y tilde of t, which is simply minus infinity to t minus tau. Okay, let us make this as tau naught, just to distinguish it from the integration variable. Let us make it t naught. So, I am shifting this by t naught. This is going to be x of tau d tau, correct, or basically I am just shifting, I am sorry, I am just shifting x of tau, I am delaying it by t naught, x of tau minus t naught. So, if I am delaying by t naught, if I delay by t naught, let us see what is the impact on the output signal. Let us set tau minus t naught equals tau tilde, implies d tau equals d tau tilde. So, this integral y tilde t will become integral minus infinity to infinity tau minus t naught. So, this will be t minus t naught, t minus t naught, integral minus infinity to t minus t naught x of 2 t, 2 t minus t naught, 2 t minus t naught x of 2 t minus t naught x of 2 t minus t naught, 2 t minus t naught x of 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 2 t minus tau tilde d tau tilde, and you can see that this is nothing but y of t minus t naught. So, if I shift the input by t naught, the output is correspondingly shifted by t naught. Hence, this is a time invariant system. Since x t minus t naught yields the output signal y t minus t naught, this is a time invariant system. Okay, so this system is a time invariant system. On the other hand, if you can look at, for instance, y of t equals t of x t equals t times x t, you can show that this is a time variant or a time varying system. You can show that this is not a time invariant, or another way to also say this is not time invariant. And that brings us to the most important class of systems, which is that of an LTI system, or let me write this clearly, this is a linear time invariant. This is what is known as the linear time invariant or LTI systems, which is probably the most important class of systems, or the class of systems that we most frequently encounter in practice, and which we are going to be most frequently interested in. That is the class of linear time invariant systems, which, as the name implies, are systems that are both linear as well as time invariant. Okay, so this, as the name implies, that is systems that are linear plus time invariant, these are known as LTI systems. Linear plus time invariant systems are known as, that satisfy linearity as well as time invariant. Satisfy linearity and time invariant properties, and these are the type of systems which we will most frequently encounter and most readily analyzed. So these are the very important class of systems. This is an important, I would say very important class of systems that we most important class of systems that we are going to frequently encounter. Okay, so this is linear LTI systems, class of LTI systems, which stands for linear time invariant systems, systems that are both linear as well as time invariant. Okay. And some other class of systems that are also important, because these are practical implications. For instance, the first one such class is the class of stable systems. Naturally, we are interested in systems that are stable and not systems that are unstable or systems that exhibit unstable behavior. From a practical perspective, interested in stability of systems, that is an important property. Okay. So, stability, let us note that down, stability of practical systems is important, correct, because in practice we would like to have a system that is stable, not something that is unstable. And a stable system is simply defined as follows. We have one definition of stability is the following thing. This is known as BIBO, or bounded input bounded output criterion. The bounded input bounded output criterion for stability, or such systems are known as BIBO stable systems, that is bounded input bounded, satisfy the bounded input bounded output criterion for stability. And the definition of that is, if a system is such that magnitude xt less than or equal to some constant c, or for a discrete time system magnitude xn is less than or equal to c. This is for a continuous time for system. This is for a discrete time system, that is input is bounded. Input is bounded, which means that input is less than some constant c. These are constants. Okay. If the input is less than some constant c, such bounded inputs produce bounded outputs, implies yt equals t of xt is less than or equal to some constant k, or y n equals t of xn is less than or equal to constant a. That is, the outputs are bounded, that is they are less than, bounded means they are basically less than or equal to some constant. Okay. So, if for every bounded input the output is bounded, so if for every bounded input the output yt is bounded, such a system is known as a BIBO stable system, that is every bounded input produces an output yt that is bounded. That is t of xt equals yt with magnitude of xt less than or equal to, just have the magnitude function over here, magnitude of yn equals magnitude of tn is less than or equal to. So, if magnitude of xt less than or equal to c, that is bounded input, implies that the output magnitude of yt is less than or equal to k. Alright. So, bounded input produces bounded output. Implies or produces bounded input produces bounded output for every input, for every such bounded input. And mind you, this has to hold for not a single bounded input, but every bounded input. This implies system is BBO stable, that is every bounded input produces a bounded output. System is a BBO stable system, a bounded input, bounded output stable system. For instance, again let us take another example here. Again a simple example will do. Let us again go back to our integrator. Y of t equals minus infinity to t x of tau d tau. Now if I consider, if I give a bounded input, that is magnitude of x of tau less than or equal to c, let us look at magnitude of y of t, which is equal to magnitude of the integral x of tau d tau, but the magnitude of an integral is less than or equal to the integral of the magnitude of the function that is being integrated, or the signal that is being integrated, which means this is less than or equal to integral of t magnitude x tau d tau, but we know magnitude x tau, this is less than or equal to c, because we have a bounded input, implies this integral is less than or equal to t. Or let us make this, since we are not, so let us make this as an integral from t minus t rather than minus infinity. So t minus t, because as you can see from minus infinity to t there is going to be a problem. So t minus t, that is an integral over a window. So this is less than or equal to integral from t minus t to t c d tau, which is equal to c tau. And now you can set this as your quantity k. So magnitude of x t less than or equal to c implies magnitude of y t less than or equal to k equal to c t. Okay, and therefore such a system therefore implies the system is BBO stable. Implies the system is bounded input, bounded output, stable. Okay, so it satisfies the BBO stability criteria. Okay, and the last class of systems finally, which we are also important, are what are known as feedback systems. And in feedback systems, what we have is an output, the output of the system, and this is also a very important class of systems, especially important from the perspective of stability. So I have a system T and I have an input xt. Okay, so what I am going to do, I have the output y of t. So what I am going to do is I take the output y of t, either directly or after suitably modifying it, I feed it back to the input. So this is the input, this is your yt is the output, yt is the output, and this is basically your feedback loop. This is basically your feedback loop. Okay, so I have an input, I have an output, and this is a feedback. So output is being fed back to the input. So output is being fed back to the input. Alright, this completes our discussion on the classification of systems. So we have looked at various kinds or various classes of systems along with suitable examples. Alright, these properties and this classification of systems is especially important to understand the behavior and properties of various systems, and also understand the various applications, right, the various important criteria from a practical perspective. Alright, so we will stop here and look at other aspects in the subsequent modules. Thank you very much.